Welcome to the deep dive. Today, we're diving into something really cool.
Oh, yeah.
A new model for separating voices in a video.
Okay.
You sent in this paper looking to listen at the cocktail party.
Right.
And it's all about isolating one person's voice, even in a noisy scene. Kind of like what our brains do, right?
Yeah, exactly.
It's like being at a party surrounded by chatter. And being able to zero in on just one conversation.
Yeah.
That's what this model aims to achieve.
That's the goal.
And what's really interesting is it doesn't just separate the voices.
Right.
It actually links them to specific faces in the video.
Ah.
So it's solving two problems at once.
Yeah.
Who's speaking AD? What are they saying?
Yeah, exactly. Traditional audio-only methods have a tough time with this. They can often separate sounds.
Right.
But they struggle to figure out which voice goes with which person in a video.
Oh, so this new model uses both audio and visual cues to get it right.
Exactly.
I read that they built a massive new data set,
Yeah.
AV speech,
Right.
to train this model.
Yeah.
Thousands of hours of video from YouTube.
Huge.
What's so special about this data set?
Well, the key here is diversity.
Okay.
They use videos with over 150,000 speakers.
Wow.
Different languages, all sorts of lighting conditions, and face poses.
So,
This means the model isn't just good at separating voices in a perfect studio environment.
right.
It's been trained on real-world chaos, which makes it much more robust.
So it's like giving the model a crash course in all the different ways humans speak and look.
Yeah,
So it's ready for anything.
exactly. Now let's get into how this model actually works.
Okay.
Imagine it has two sets of eyes, one for audio and one for video.
Okay. I'm picturing that. What do these eyes see?
The visual eye focuses on faces, but not just the whole face.
Okay.
It uses face embeddings from a pre-trained face recognition model. Think of these embeddings as numerical representations of facial features.
So it's kind of like the model has already learned what's important about faces from a different model?
Exactly. This helps it zero in on the parts of the face that matter most for speech separation.
Okay.
The audio eye, on the other hand, processes the sound into something called a spectrogram, which is like a visual representation of the different frequencies in the sound.
So it's taking something we hear
Yes.
and turning it into something the model can see, right?
That's a great way to put it. And then the model uses all this information, the facial cues and the audio frequencies, to create what we call masks.
Okay.
These masks act like filters that separate out the individual voices.
So it's like applying a custom-made filter for each speaker, letting only their voice through.
Precisely. And the really cool part is that it can handle multiple speakers at once.
Oh, wow.
If there are 3 faces detected, it creates 3 separate masks, one for each person speaking.
I'm curious.
Yeah.
Does it need a separate model for each number of speakers? Like one model for 2 speakers, another for 3, and so on?
They did train separate models for different numbers of speakers. But here's the surprising thing they discovered.
Okay, tell me more. What did they find?
They found that even if you use the single speaker model on a video with multiple speakers, it still does a remarkably good job.
So it's like having a Swiss Army knife of voice separation.
Right.
No matter how many people are talking, this model can give it a shot. Now, I know they tested this out in some pretty challenging scenarios, right?
Yes, they really put it through its paces. They wanted to see how it would perform in situations where separating voices is incredibly difficult, even for humans.
Okay, give me an example. What kind of situations did they test?
One example was a video called Double Brady, where 2 different people are saying the exact same words in unison.
Oh, wow. That sounds like a nightmare to try to separate. How did the model handle that?
Remarkably well, actually. It was able to distinguish between the 2 voices and create separate audio tracks,
Okay.
even though they were speaking the same words simultaneously. They also tested it on videos with heated interviews, noisy bars, and even screaming children.
It sounds like they threw everything they could at it.
Yeah.
So even with all that chaos, how did it perform?
Overall, the results are quite impressive.
Okay.
It consistently outperformed state-of-the-art audio-only models in these challenging scenarios.
But I imagine there are still some limitations, right? Even our own brains struggle to filter out noise sometimes.
You're absolutely right. While this model is a significant step forward, it's not perfect.
Yeah.
They found that in extremely noisy environments, like a really loud bar, the separated speech quality wasn't quite as clear.
That makes sense. There's only so much you can do when the background noise is overwhelming. But still, it's pretty amazing that it can even attempt to separate voices in those situations.
Yeah.
Now, you mentioned that the model uses visual cues from faces.
Right.
Did the researchers look into how much it relies on those cues?
They did. And that's where things get even more interesting. They did a clever experiment where they blocked out different parts of the face in the video and saw how that affected the model's performance.
So they were basically testing, can it still separate the voices if it can't see the mouth clearly? Or what about if the eyes are covered?
Exactly. And as you might expect, blocking the mouth had a big impact.
Yeah.
The model relies heavily on lip movements
to
analyze speech patterns. But here's the surprising part.
Okay. I'm on the edge of my seat. What did they find?
Blocking other areas like the eyes and cheeks also affected the model's performance, though to a lesser extent.
So even subtle facial movements beyond just the lips are giving the model information about what's being said?
It seems to be.
That's wild.
It really is. It suggests the model is picking up on more than just the mechanics of how the mouth moves when we speak.
Right.
It's almost like it's learning about facial expressions and how they relate to speech.
So it's getting closer to how we actually communicate, where it's not just about the words, but also the nonverbal cues. It's not just hearing, it's seeing the whole picture.
Precisely. Now, they also tested what happens when you gradually reduce the amount of visual information.
Okay.
And what they found is quite remarkable.
I'm all ears. What happened when they took away the visuals bit by bit?
The model's performance degraded gracefully. It didn't just fall apart without the full video.
That's impressive. You'd think it would rely heavily on seeing every detail of the face.
Right. It seems to be capturing something more fundamental about speech patterns. It's analyzing how sounds change over time, not just what the mouth is doing at any given moment.
So it's almost like it's developing a sense of rhythm and flow in speech.
Yeah.
Which allows it to make better predictions, even when it's missing some visual cues. That's a big leap forward.
Absolutely. And this ability to capture those temporal patterns opens up some really interesting possibilities for how this technology could be used.
Okay.
One application they explored was video transcription.
Okay, tell me more about that. How does this model help with transcribing videos?
They found that when they used the model's separated audio, YouTube's automatic captioning system produced more accurate results.
That's a huge deal. Accurate captions are so important for accessibility.
Right.
It could make a big difference for people who rely on captions to understand video content.
Exactly. Now, we've talked about the model's capabilities, the data set, the experiments, but I know what you're really thinking.
You know me too well. The question on my mind is, can we get this working in real time? Imagine live video conferencing where everyone sounds crystal clear, even with background noise.
Right.
Or maybe even hearing aids that can filter out everything except the person you're talking to.
Those are some amazing possibilities, and it's where a lot of the excitement around this research lies.
Yeah.
But there's some hurdles to overcome before we get there.
All right, let's talk about those hurdles. What needs to happen to make this real-time dream a reality?
The current model is designed for offline processing, meaning you apply it to a video that's already been recorded. For real-time applications, we need it to work on the fly as the audio and video are coming in.
So it's a question of speed, right? The model needs to be able to process everything quickly enough to keep up with a live feed.
Exactly. We need to address two main things.
Okay.
Computational efficiency and latency.
Okay, break those down for me. What do those terms mean in this context?
Computational efficiency means making the model run faster, using less processing power.
Okay.
Right now, the model relies on deep neural networks, which can be very computationally intensive, especially when dealing with both audio and video.
So it's like trying to cram a ton of processing into a tiny space. We need to find ways to make it leaner and meaner. What about latency?
Latency is the delay between the input and the output. So in this case, it's the time it takes for the model to process the audio and video and produce the separated audio streams. For real-time applications, that delay needs to be as small as possible, ideally imperceptible.
So if you're in a live conversation, you don't want to hear the other person's voice coming through with a noticeable delay. It would make the conversation feel disjointed.
Exactly. Now, researchers are exploring a lot of different approaches to tackle these challenges.
What are some of the strategies they're looking at?
On computational efficiency side, one approach is to explore more efficient neural network architectures.
Okay.
This could involve things like model compression, where you essentially shrink the model down to a smaller size without sacrificing too much accuracy.
So it's like finding a more compact way to package all that processing power.
Exactly. They're also looking at quantization, which involves using lower precision numerical representations.
Okay, so it's like finding clever ways to optimize the code and the way the model handles data to make it run faster. Are there any other tricks up their sleeves?
Another big area is leveraging hardware acceleration. Specialized hardware like GPUs and TPUs are designed for the kinds of computations involved in deep learning, and they can provide a huge speed boost.
So it's not just about making the software better, it's also about having the right hardware to handle the workload.
Absolutely.
Hmm.
And as hardware technology continues to advance, we can expect to see even more powerful tools for accelerating these kinds of models.
That's encouraging. It sounds like there's a lot of potential for improvement on the computational front. What about latency? How are they trying to reduce that delay?
One key approach is to develop algorithms that can operate on smaller chunks of data.
So instead of processing a whole video at once, you'd break it down into smaller segments and work on them in parallel.
Exactly. This can significantly reduce the overall processing time and minimize the delay between input and output.
And I imagine this becomes even more important in live applications where you need to keep up with the incoming audio and video stream in real time.
Absolutely. There are also techniques for predicting future audio and video frames.
Okay, now that sounds really futuristic. How do you predict something that hasn't happened yet?
It's not about seeing into the future literally, but about using patterns in the data to make educated guesses about what's coming next. This can help compensate for any inherent delay in the processing pipeline.
So it's like giving the model a little bit of foresight, allowing it to stay a step ahead.
Precisely.
Yeah.
Now, all of that said, achieving truly real-time performance with this level of complexity is still a challenge. But it's a challenge that researchers are actively working on.
It sounds like there's a lot of exciting research and development happening in this area.
There is. And as those efforts continue, we can expect to see more and more applications of this technology emerge in the real world. But it's not just about making the technology faster and more efficient.
Right.
There's also the user experience to consider.
That's a good point. What are some of the key things to keep in mind from a user experience perspective?
In real-time applications, it's crucial that the separated audio sounds natural and doesn't introduce any distracting artifacts.
Right. You wouldn't want the separated voices to sound robotic or distorted. It would defeat the whole purpose of creating a clear and enjoyable listening experience.
Exactly. So preserving the original pitch and timbre of the voices is very important. And in live situations, you might have background noise that's constantly changing.
That's true. A noisy coffee shop or a busy street corner could really throw a wrench in the works.
Right. So the model needs to be adaptable and robust to handle those variations in background noise. Another user experience consideration is control.
Control, what do you mean by that?
In some applications, you might want to give users the ability to adjust the level of separation or even select which voices they want to focus on.
Oh, I see. So instead of just having the model automatically separate everything, you could give users the power to fine-tune their listening experience.
Exactly. Right. Imagine attending a conference and being able to adjust the volume of different speakers or even mute those who are just adding to the background noise.
That would be amazing. It's like having a personalized audio mixer for any situation.
Precisely. Giving users that level of control can significantly enhance usability and make the technology more adaptable to different needs and preferences. Now, we've talked about the technical hurdles and the user experience considerations.
It's really fascinating to see how all these different pieces fit together, but I'm wondering if there's anything else we need to be thinking about as this technology moves towards real-time applications.
There's one more important aspect to consider, and that's the broader context in which this technology will be used.
Okay. I'm intrigued. What do you mean by the broader context?
Well, this research is part of a larger trend in AI, where we're seeing models that can perform tasks that were once thought to be exclusively human.
We've got models that can translate languages, write different kinds of creative content, and even compose music. And now we're talking about a model that can untangle the nuances of human speech in a way that's pretty mind-blowing.
Exactly. It's pushing the boundaries of what we thought was possible with AI. But as we develop these powerful technologies, we also need to think about their impact on society.
So it's not just about the technical achievements, it's also about how this technology will be used and what kind of world it will create.
Precisely. We need to consider the potential benefits like improved accessibility and communication, but also the potential risks.
What kind of risks are we talking about?
For example, imagine if this technology were to be used for surveillance purposes. The ability to isolate and analyze individual voices could raise some serious privacy concerns.
That's a good point. It's important to make sure this technology is used responsibly and ethically.
Absolutely. And those conversations need to happen now as the technology is being developed, not after it's already out in the world.
It's like we're not just building a tool, we're shaping the future. Yeah. And we need to make sure it's a future we want to live in.
I couldn't agree more. Now, as we wrap up this deep dive, I want to emphasize that this research is really just the beginning.
I'm ready for more. What else do we need to explore?
Well, we've talked about separating voices, but imagine a future where AI can understand not just what we're saying, but how we're saying it. Think about recognizing emotions, detecting sarcasm, even understanding subtle nuances in tone and inflection.
That would be incredible. It would take communication to a whole new level.
Exactly. And this research is a stepping stone to those kinds of advancements. It's paving the way for a future where AI can truly understand and interact with us in a more human-like way.
It's a future I'm excited to see unfold. This deep dive has been a wild ride, and I feel like I've gained a whole new perspective on the power of AI and its potential impact on our lives.
I'm glad to hear that. It's a field that's constantly evolving, and there's always something new to learn and explore.
Thanks for joining us on this journey into the world of audio-visual speech separation. If you want to learn more, we've included links to the Research Paper Project website and some example videos in the show notes. Until next time, keep exploring, keep questioning, and keep learning.
See you next time.